All right, so here's the problem. We have a controller, and we want to move our character in the direction we're aiming, which is the controller's direction. It's the direction the controller is facing. Now, a controller doesn't inherently have a forward vector per se, but it does have a rotation. So our job is to try to get the forward vector of the controller. In other words, we need to look at the controller's rotation and find out what the forward vector would be corresponding to that rotation. Now, we know that our controller's rotation has a yaw, pitch, and roll. So if our controller itself rotates upward, let's say by 45 degrees, then we know that its forward vector would be pointing upward by 45 degrees. And this would also tilt its z-axis by 45 degrees as well. And we know that the control rotation would have a yaw and pitch of both 45, whereas the roll would be 0. So the question becomes, how do we get a forward vector using this information? Well, one of the mathematical tools that we can use to do this is the rotation matrix. A matrix looks like this. It has rows and it has columns. And a matrix in mathematics can be used for all sorts of different things. The rotation matrix is just one particular application of this mathematical tool. And you might notice some sine and cosine functions in this rotation matrix. So where did these come from? Well, let's take a very simple example. We have two-dimensional space, an x-axis and a y-axis. And let's say we have a vector called v, and the vector is pointing in the x-axis direction. We'll pretty much call this the baseline position for this vector. And we know that the vector v has a magnitude, and we'll call that v, and we can see that right here by this symbol. Now let's say that we rotate the vector. We're rotating upwards away from the x-axis by some angle, which we'll call theta, okay? So if we're rotating our vector above the x-axis like this, then what is the resulting vector? What is this new vector, which we'll call v sub t, t standing for transformation. So we've rotated the vector by theta, and in order to calculate this new vector's x and y components, we need to know this particular length, in other words, the y component of this vector, and we need to know this particular length, which is going to be its x component. So we can say that this length here is x, and this length here is y, where our new vector, v sub t, has x and y components, x and y. Now, how do we get x and how do we get y? Well, we do know about the sine and cosine functions, and we know that this particular vector forms a right triangle. Here is the right angle, right? And if we take the sine of theta, well, what do we get? We can take sine of theta, and we know that the sine of this right triangle is this length here, which happens to be y, divided by the magnitude of this vector, which happens to be this quantity here. And if we solve for y, then this tells us that y is equal to the magnitude of the vector times the sine of the angle. Now, what about x? Well, we can take the cosine of theta. Let's see what we get there. So cosine of theta is equal to the adjacent side of the triangle, which happens to be x, divided by the hypotenuse, which happens to be the magnitude of the vector. So we can solve this equation for x, and x turns out to be the magnitude of the vector times cosine of the angle. So this gives us our x and our y for the vector. So we do know that sines and cosines are somehow coming into play here when it comes to figuring out what this resulting vector is after rotating it up by some angle theta, right? Well, this particular example is one application of a rotation matrix. You just can't see the matrix. It's sort of hidden in the math. Well, mathematicians, clever as they are, have come up with a formula for two-dimensional vectors in a compact little form known as the rotation matrix. And the way to get this result by taking some vector and using the rotation matrix to transform it by rotating it by some angle theta is as follows. We take the rotation matrix and we multiply it by a vector. Now, this might seem confusing. How do you multiply a vector by a matrix? Well, I'll show you. Let's consider for a moment that v is a unit vector, which means that its magnitude, the magnitude of v, is simply 1. Well, in that case, we know that y equals the magnitude times sine of theta really just means that since v is 1, y equals sine of theta. And if v is 1 here, then we know that x is cosine of theta. And if that's the case, then our original vector is simply the vector 1, 0. Now notice I'm writing the vector as a column now, instead of what we see here, an ordered pair. Now if we write our vector as a column, now it's in the form where it can be multiplied by a matrix. So let's use our rotation matrix by multiplying our vector 1, 0. 1 in the x, 0 in the y. So here's how we do it. We take our vector 1, 0, and we multiply by the rotation matrix, which is cosine of theta, negative sine theta, cosine theta. Now here's how you multiply a vector by a matrix. You take the vector, and you take the first row of the rotation matrix, and you perform multiplication of the first terms, and you add the multiplication of the second terms. In mathematics, this is known as the dot product of the vector by the first row. So let's do that. So the result of this rotation matrix is going to be equal to the vector whose first element is this dot product. So we take 1 times cosine of theta, which is cosine of theta, plus 0 times negative sine theta, which is 0. So that's the first element of our result. Then we take the vector and we take this dot product with the second row of the matrix. So we take 1 times sine theta, which is sine theta, plus 0 times cosine theta, which is 0. And the result of multiplying this vector by the rotation matrix gives us this vector. But we already determined that x is cosine theta and y is sine theta. And of course, this is the vector x, y. So we see that this is a particular example of rotating a vector by the angle theta. Now, this is a two-dimensional version of the rotation matrix. There does exist a version of the rotation matrix in 3 dimensions, where you can multiply a 3-dimensional vector by a 3 by 3 matrix. This is a 2 by 2, and you can pass in some angle and get a vector as a result, rotated by that angle. In Unreal Engine, we have the ability to create a rotation matrix and use angles to create a vector corresponding to that rotation. Now, if our controller starts off with 0, 0, 0 for its rotation, yaw, pitch, and roll are all 3 0, then as we rotate the controller and change its yaw, pitch, and roll, we have 3 angles, 1 for the yaw, 1 for the pitch, and 1 for the roll. And we can use rotation matrices to find the vectors corresponding to those x, y, and z directions of that rotation. So this is how we can find the forward and the right vectors of our controller's rotation. Now, all of this is just theory behind the scenes. We're going to use simple functions already built into the engine to do this for us. But now that you've seen what goes on under the hood, you'll have a better understanding of what those functions are doing for us. So let's jump in the engine and do this.